Hello, everyone. Good evening. Welcome to the newest edition of DevDay. DevDay is a monthly. Actually, we have more than one talk a month in a few months now. It's an event organized and conducted by Sahaj. We have a variety of topics in DevDay, including research and development topics on data science, artificial intelligence, machine learning, as well as a variety of topics in platform engineering, data engineering, and whatnot. So today, I'm going to be the speaker. My name is Karthika Vijayan, and I will be talking about one of the research activities that we have conducted at Sahaj as part of as part of an initiative called Sahaj Labs. And this edition of DevDay, we have this topic related to natural language processing. So I will start now. I hope everyone can see my screen.
Yes.
Thank you. Yeah, so the title of today's topic is Multilingual Information Extraction from Short Text Messages. Right. And I will just do a little intro of myself. My name is Karthika Vijayan. I am a solution consultant with Sahaj AI, and I predominantly work in data science. My area of expertise are speech and audio processing and natural language processing. I have also my bachelor's and master's education are in electronics and communication engineering, and I have a PhD in speech processing and applications. And today I'm going to talk a very specific topic in natural language processing and in a multilingual scenario. So the flow of today's talk is I will just do a quick introduction to multilingual NLP, NLP being natural language processing. I hope everyone also already knows that. Then we will do a quick recap of language representation models and how can they be used in multilingual setting, multilingual applications. Before delving into the actual crux core of today's talk, which are conversational assistant or information extraction for conversational assistant, I will briefly touch upon an initial experimentation that we have conducted in multilingual NLP, which is text categorization, which kind of led us to this, which was the predecessor experiment that led us to this information extraction experiment. Then I'll conclude. So let's do an intro. Okay. What is NLP to begin with, right? NLP intends to make a computer understand a language. And when I say understand a language, there are a lot of rules which are associated with each language, right? So there is a syntax for the language, there are semantics, there are grammar associated with each language. There are different sentence constructs which are ruling a language construct. Then there are contexts in which a word can appear and a word cannot appear, etc. So when the NLP intends to make a computer understand or learn a language by multilingual NLP, of course, it is a general extension. We want an AI or a computer to understand multiple languages. Now, the challenges are multifold because different languages are guided by different rules and different settings. So now we want one system or one pipeline to understand and learn multiple languages. So it poses multiple challenges. There are, of course, similarities between different languages that we can leverage upon to make this multilingual NLP possible. But of course, the dissimilarities or the differences between languages also makes it a little bit of a challenge. To add on to the set of challenges, we know that when we converse, when we type in social media or an email, we generally do not actually constrain ourselves to this very strict set of rules, right? There is a conversational style of communication that will come into text messages as well. So this again goes contradicts with the rules of that particular language, making the natural language processing much difficult. Uh, and then again, we have regional accented parts coming into when into our language when we converse, when we talk, when we text. For example, we generally use Hindi words or your mother tongue words in between English. This results in a situation called code switching. Then there are very particular situations like regional Singaporean English, where this what do you call it? It's very funny. The people generally type la at the end of every sentence. So those are the regional constructs that creeps into a pure language scenario. So all these poses challenges in multilingual NLP, whatever be the task or whatever be the application that you are looking into. So an ideal setting to make multilingual NLP possible or realized is we build a language agnostic system. What I mean by a language agnostic system is one system that can realize NLP tasks without having to go through any language specific steps. For example, in the figure shown, if I am building a text categorization system for taking in strings of text and putting into right categories, like Maharashtra CM resigns to be in the class of politics, or it's in the political news category, as opposed to this Hindi string where it talks about Virat Kohli scoring a century. It has to go into the sports category, or the Malayalam sentence which is talking about film awards, state film awards. I would like that sentence to go into the entertainment category. And I want one system. I am building just one text categorization system to take in inputs from all these languages and still deliver the desired functionality. So this is a language agnostic system. So ideally, if we can develop a pipeline that can be utilized for multiple languages without any additional processing, without any language processing steps, that would be the best case scenario for realizing multilingual natural language processing. Why multilingual NLP? I think the answer is like it's self-explanatory. Individuals in multilingual societies converse in multiple languages. India being a rich multilingual society, we have 22 scheduled languages in India and several unscheduled ones. And if you look at into the world, right, there are approximately 7,100 languages being spoken around in the world. So if you're building an AI, if you're building an intelligent assistant, the natural progression is, of course, you want that assistant to learn and understand multiple languages. So if you look at the legacy systems for a little bit, traditionally what we used to do is we will have language specific models and language specific system catering to each language, and then we will have to build multiple language specific systems to cater all languages under consideration. But if we plug our attention to multilingual NLP, if we have pre-trained resources, which we will touch up in a moment, we to make that system work, we generally do not require huge amount of language specific resources, be that data, be that labeling capacity, etc. So multilingual NLP is beneficial in multilingual settings in designing several applications, like a conversational assistant, like a customer care, automated customer care assistant, right? If I'm complaining that I'm not getting my internet properly, same thing I can complain in my mother tongue, which is Malayalam. And I would like that assistant to give me appropriate response in my own language. Similarly, if you look at another application like a banking scenario, an automated assistant to assist you with the banking, you would like that assistant to answer your queries about a car loan or a home loan, whatever the language be you are conversing in. Automatic management of archives is another huge application. Like you can think about the media houses, and the media houses in India publishes newspapers and other visual as well as audio media content in multiple Indian languages. And if you have one system to maintain the archives, be it English news, be it Hindi news, be it Tamil, Telugu, or whatnot, that is highly beneficial, of course. Then code switching, as I mentioned, we have a general tendency to mix and match multiple languages, right? And if we have a sentiment analysis or a sentiment classifier or a social media analyzer, which is multilingual NLP, and that can take care of these code switched sentences, that would be ideal as well. So this is why we should go for multilingual NLP rather than language-specific resources. Having said that, I would like to say language-specific models, if they are properly built with proper amount of training data, that will any day outperform multilingual systems, because multilingual systems have to learn multiple languages, whereas as opposed to the language-specific system, which will just concentrate and learn one particular language. How to perform a multilingual NLP. So we have visited the what's and the whys. Now let's talk about how, which is the most important thing, right? I would just quickly recap on the legacy systems, which generally use language specific modeling. If you have 5 languages under your consideration for one particular application, you have to actually build 5 different language models, then put a language detector like a switch in the front end to identify the language and route the queries to the corresponding language model for further processing. As I already explained, this is a tedious task. You have to find all the data from 5 languages. You have to build your own language-specific models, and then also you have to build a language detector, which in itself is not an easy task. Then another strategy, which was like the widely used strategy, even now people use it, is build one language specific model, preferably in English, because data, it is easier to find data, it is easier to find pre-trained pipelines, etc. And then use a translation. So if you want an NLP to answer your query in Hindi, first you transfer it into English, do all the NLP based processing, and finally, once the answer in English comes out, the output in English comes out, translate it back into Hindi. So this is, again, as I said, it's a widely used strategy. But the problem here is, as you might have already seen Google Translate, right? It's not ideal. Many a times, the translation systems messes up the functionality. It may destroy the sentence context. It may destroy valuable information, etc. And there is an error which is attached to the translation strategy, which will get added into your NLP pipeline, which has an error metric of itself. So this will lead to error propagation. Again, it's not an ideal strategy for multilingual natural language processing. The third strategy is like the groundbreaking one, which is transfer learning. I'm quite sure that many of you already know what transfer learning is, but bear with me for in the interest of the general audience. I would just quickly touch up what transfer learning is. So transfer learning is basically you have a model or a pipeline which you have trained with ample data resources, ample labeling efforts for a particular task, for a particular domain, and for a particular input. In our case, let's just say for one language. Now, you want to take this system and use it for another language. For example, let's imagine this model that is shown in the figure is a neural machine translation. And I am looking to translate Hindi to English. Uh, um, and now my interest or now my application wanted a Hindi to Marathi translation. So I will try to tie up this whole pipeline. First, I'll have a neural machine translation for Hindi to English, and the next neural machine translation from English to Marathi. Um, and I will not actually cascade 2 systems. It will mostly a little bit more of an intelligent strategy of reusing parameters, reusing hidden layers, intelligent pre-processing, intelligent post-processing, etc. So this kind of transfer learning is actually a part of the transactive transfer learning, which is the transfer learning between feature spaces. So initially you have assigned XS and XT as the feature spaces. They come from the same setting, same dimensional feature space. Now for your target application, the feature space itself has changed. So this is a classic example of transfer learning. And in our case, this is actually cross-lingual transfer learning. A second type of transfer learning is imagine you have trained a system for text categorization or any application for one particular type of articles in the same language. For example, I want to tag medical articles published in English, medical journals published in English. Now I want that same system to tag sports articles published in English itself. So that's a domain difference. Sports from medical terminology, medical vocabulary to sports. So this is a domain transfer. And the third one is actually inductive transfer learning. We will not go into detail. It is like you have actually constructed a system for one particular application. Let's say topic categorization, which we have already seen, right? Now I can actually take the front end of that system, remove the back end of the system, plug it with another set of classifier, another set of labels, fine tune it, and use it for sentiment classification. So that is a task transfer. Now, in a general setting of multilingual NLP, we have to plug and play with multiple of these cross-lingual transfer, domain transfer, and task transfer. Okay, so this is general transfer learning. Now we have to talk about language representation models because if you look at a NLP pipeline, right? This is the most important thing, which is actually generating a numerical representation or mathematical representation of your language, which is typed in text. Okay, so what we are looking at is an embedding generator. This could be most commonly used architecture. It is going to be a transformer architecture, which has an encoder and a decoder representation, which is actually trained for one particular task, most commonly master language model. What master language model does is it will take, I am not going into the detail of transformer architecture and multiple architectures because that is an NLP course in itself. So let's talk about a transformer architecture, which is just an encoder and a decoder representation. Now, Google's BERT is the most famous and the most commonly used transformer architecture for language representation. What it does is that while training, it actually sees a huge amount of data, billions of tokens, millions of unique words in English, of course, and then 15% of words are always masked. It is just blanked out, and the model, the transformer architecture, is actually trained to predict the next word, and it will build upon it. It will start with one sentence, two sentences, and finally it will see billions of tokens, and it will train itself to generate an efficient representation for each word, and it will look at all the neighboring words. It's called positional encoding. It will also see the context of that word from multiple occurrences in that huge database. In a way, in other words, we can say that it will actually learn the meaning of the word, the context in which that word can occur in English, and it will give you a number or a vector representation. It's a mathematical representation. So that's how it generates natural language representation model for a particular language, right? Now, what we can do is we can actually take this BERT embedding, which is just an encoder architecture, check out the post-processing side. There is a fully connected layer and whatnot for the next word prediction. Now you can actually take that embedding extractor or encoder representation, plug it with a classifier layer or a couple of classifier layer, and use it for topic categorization in English. And a multilingual natural language processing model for language representation model is a natural extension. What you do is you take a BERT architecture, which already has this positional encoding, which will look into the both directions of neighbors around the word, and it will see actually data from multiple languages. In fact, multilingual BERT released by Google in 2018 have seen multiple, a huge data set from 104 languages, if I'm not wrong. Okay, so what it does is it will just predict the next word and learn that language while doing so. So it will learn English first, then Hindi, then all 100 languages. So the little bit of what do you call it, the trick or a little bit of fine tuning or conditioning that Google did is it took all the Wikipedia articles belonging to these 104 languages And while doing so, what can it ensure is that there is some amount of parallelism between the Wikipedia articles, right? For example, if you talk about Sachin Tendulkar, cricketer, there will be a Wikipedia article attached to Sachin Tendulkar in English, in Hindi, in Marathi, and even in other foreign languages. And a Wikipedia article about Sachin Tendulkar will talk mostly, roughly about the same things: how many centuries he scored, how many matches he played, where is he born, what's his birthday. These things are going to get repeated in multiple languages. So the bird, multilingual bird, sees individual languages and learn those languages, and also it leverages for this some amount of parallelism that is ensured in the database, so that it can actually make that associations, one-to-one associations between English and Hindi and Marathi, so that while you use it for multilingual setting in the future, it will still give you good, faithful language representations or word embeddings. Um, Facebook actually took it to little further. They used a cross-lingual pre-training also on top of a BERT architecture. Their BERT is called Roberta, which is a robustly trained BERT. And they used an additional step of cross-lingual pre-training. And their language model has a language representation of 100 languages on much more data than Google's Embed. Embed is trained on Wikipedia articles, whereas XLMR is trained on common crowdsourced data. It's crawled data. So that is all about language representation model. So basically what it does is it gives you word embeddings, which captures the meaning and context of a word from a large, which it learned from a large database. Now that we know that we have this language representation model, which can act as the core of any NLP pipeline, let's talk a little bit about a language agnostic pipeline. I'm going not a pipeline can be as elaborate as you want, depending upon your task, or as simple as you want. It's mostly how you design it. So I am going to talk about a very simple pre-processing, post-processing, and the featureizer pipeline. Because going to finer details is not the intention of this talk, right? So in pre-processing, there is a tokenizer, which is always there, which basically cuts a sentence into individual words. And since we are talking about most of the languages, including most of the Indian languages, are words white space separated. So we put a space in between two words. So a white space tokenizer is good enough for most of the Indic languages that we are interested in. And this is, of course, language independent. You just have to look for white spaces and cut long sentences into tokens, and tokens being words in our case. Then think about the post-processing. For example, a classifier. If it is topic categorization that you're talking about, it is a classifier in the backend, right? What does a classifier work on? It just works on embeddings or vector representations. It doesn't care whether the language is English or Hindi or Marathi or Malayalam and whatnot. It just takes in a set of vector representations, set of vectors, and classifies it depending upon if it is a supervised classifier, depending upon the labels that you have provided. So the only component that we have to focus on, that we have to keep our attention on, is the featureizer. And we have actually already seen the language representation model, right? This is a good enough featureizer for multilingual setting, because it actually have understood and learned 100 languages. So we can actually use this to build our pipeline. Now, there is a small crux here, okay? Even though we talk about these language representation models as pre-trained resources, they have actually seen context and meanings and sentence constructs from the database that is provided to them while training. In Google's case, it is Wikipedia articles. In Facebook's case, it is crowdsourced data, most probably from entities that Facebook owns, right? The Facebook posts that we make, Twitter, or other crowdsourced data. So now it has seen this huge database, agree. But if we want to actually port this and use it in a particular dedicated application that is of our interest. For example, a conversational assistant, which will, I own a business and I want a conversational assistant to assist with the sales. Then it is not guaranteed that this model, these pre-trained models that are Embed or XLMR, has actually seen the context of the text or the language that is going to be coming in my case, which is very application specific. This is a classic example of domain mismatch or domain transfer that we have to think about. So if I want Embed to work in English, Embed of course works in English because it is being trained on English. But if I want Embed to work in my particular business application, which is a sales assistant, which can answer to queries regarding the product that I manufacture and sell out, I have to actually show a little bit of data from my application to Embed so that it can actually fine tune on top of that data. And so it, or of course, leverages on already existing information or already existing knowledge in it. And it also tunes itself to cater to my business application, which is very, which has a specific set of vocabulary, which Embed may not have previously seen, right? So a fine tuning of any of these pre-trained models for the task we need, for the domain we need, and for the language we need is definitely required. This is again a non-fact. I was just mentioning it. So before going to the conversational assistant and information extraction, for the purpose of a conversational assistant, I'll just quickly touch upon one of the first experiments that we did, which is topic categorization. Again, topic categorization is not a very difficult problem because most of the cases in topic categorization is like, for example, the news articles categorization, we have ample amount of data, at least a paragraph, which we need to decide whether it belongs to a particular category of like business or politics or a medical article, right? So it's not a very difficult task. So for our experiment, we took this Indic NLP dataset, which is an open source dataset out there, which has news articles belonging to multiple languages. Okay. And categories of the news articles are something like business news, political news, news on politics, entertainment news, sports news, etc. And we need to classify the articles into corresponding category. So this is again a case of task adaptation. Remember that Embed is actually trained for predicting the next word, but we can actually take the embedding extractor, which is the encoder representation, and plug in our classifier at the back end of it, and then just fine tune it for a little bit of data and measure the accuracy or deploy for the particular application. So of course, the pre-processing is pretty much very simple embedding extractor that we can use either Embed or XLMR. And finally, we have plugged in classifier layers at the back end of the system. And we noted accuracy as our metrics. So now this experiment is again not that, it's not like the groundbreaking experiment. People already know it. So what we did was we took news articles in Telugu and fine-tuned XLMR with labels. It is a labeled data set. So I know which all articles belong to business category. I know which all articles belong to entertainment category, so on and so forth. Okay. So what we observed was when we fine-tuned the XLMR with Telugu and tested it on a test case, which is not part of the training data, we got above 90% accuracy for all the languages that we experimented with, Telugu, Tamil, and Malayalam in this case. All of them got 90% classification accuracy or categorization accuracy, which is not surprising. We already know that XLMR has seen good enough data from each of these languages, and we just did a domain adaptation. We just asked it to actually see the context and see the association of these particular embeddings to the word, the category levels. So we have seen it, we have shown it a little bit of training data, which is used for fine tuning, and we got a 90% accuracy. No issues here. Now, what we are interested in is the problem statement is going to take a little bit of a turn here. excuse me. So the problem statement is going to get a little bit of a turn here. Imagine, a multilingual society like India, right? If we compare the amount of media, visual, audio slash text um, media out there, we could actually see that it is very skewed. So a language like Hindi will definitely have more resources available out there, just because of the sheer volume of population that speaks and converses in Hindi in India, as opposed to a language like Malayalam, which is my mother tongue, which is being spoken in a smaller state called Kerala, and its population is much less than the Hindi-speaking population, because Hindi is being spoken in multiple states in India, right? And here we can talk about low resource languages. So in a general context, in a practical scenario, there are definitely going to be high resource languages and low resource languages. So even for the purpose of fine tuning, I agree that all these models like XLMR, Embed, etc., have seen actually enough general context data. I would call it like general data, because it's not very catered towards a particular application in hand, like, for example, my business application. Then even to fine tune a model like that, it is not necessary that I have all the data that is required to, the appropriate amount of data that is required to fine tune these models available in all the languages that is of interest to me. So if I can still use fine tuning data from Hindi, which is out there, and maybe it is easier to get labeled, get a supervised training data set ready, and only use that to train or fine tune this particular model, and use it as a transfer learning for multiple other languages. Then this is the cross-lingual transfer that we have talked about earlier. So we just did this very basic experimentation. We retrained or fine-tuned this particular XLMR based model, whose task was topic classification. So we already did that task transfer already. Then we are now doing a cross-lingual transfer. So we showed it or fine-tuned it, XLMR based model with Malayalam data only, to perform the task of topic categorization. And we tested it on multiple other languages. Okay. And not this was like a little bit of surprise. So Telugu and Gujarati gave above 90% accuracy. Just notice again that the training or fine tuning is only done with Malayalam data. And Telugu and Gujarati performed better, 90% accuracy. Okay. There is some similarities, linguistic similarities between Telugu and Malayalam. So that's kind of justifiable. Gujarati is a little bit of it's not very linguistically similar to Malayalam. On the other hand, Tamil is very, very linguistically similar to Malayalam, and still it gave only 43%. Okay, 43 is still a good score, because this is zero shot learning. So basically our model for this particular topic categorization has not been fine-tuned on Tamil data. So if it is a general case zero shot learning, 43 is still a good number. And Punjabi, which is again not linguistically similar to Malayalam, also gave 43%. So now we have something to explain, right? So this is interpretation. So this is where the analysis and the research comes in. So two languages which are similar to Malayalam, Telugu and Tamil, gave very different results. Two languages which are very dissimilar to Malayalam, Gujarati and Punjabi, also gave very dissimilar results. So linguistic similarity is not a constraint here. It's not the contributing factor to this table, this set of results in the table. But one would, the linguistic similarity is the first thing that you will think of when you are doing cross-lingual transfer, because that is one limitation or one sort of restriction that was put on transfer learning in the earlier days, when it was invented. When the transfer learning was studied in between two languages, there are multiple research papers which talks about how to choose those pair of languages based on linguistic similarity, predominantly based on linguistic similarity, so that you can actually build on one-to-one associations between phrases, between grammars, and between general rules that governs the language construction. Okay, so this is a very difficult result to interpret because we kind of exhausted our options in terms of linguistic similarity right there. Then what we noticed was, we of course did the enough data analysis. What we noticed was Malayalam data in these cases had four classes: business, sports, entertainment, and politics. I may be I may be a little wrong here in the specifics, but Malayalam data has four classes, and we did the topic categorization. And Tamil data, even though it is linguistically similar to Malayalam data, we found that it had an additional class. I don't remember which one specifically. Probably it was politics, which was not part of Malayalam data, but the whole system was topic categorization, right? So there was a class mismatch, output class mismatch. So that is one contributing factor. But why? Right? Because our friend end, which is XLMR, is supposed to give you good language representation, and we are actually fine tuning with respect to class mismatch, the classes. So we did a little bit more digging, and we actually found this notion of inherently parallel data. How these models, be it XLMR, be it Embed, or even BERT in case of English, right? It actually learns the meaning of a word, meaning of a sentence. It gives you sentence embeddings, it gives you word embeddings, it learns from the context. So this notion of inherently parallel data came up. So I'll just explain what this. So we all know what parallel data is. This used to be one important constraint to build any neural machine translation systems in the earlier days. You should have same sentences in English and Hindi to build a system that can translate English to Hindi. Okay, so this is parallel sentences. I would like to know the price of this car. So this is a sort of a query a conversational assistant or a sales assistant will receive from a customer. And similarly, the exact same sentence could be there in Hindi. मैं एक कार की कीमत जानना चाहूंगा. So it's exact same sentences. But in practical situation, in real world, right, it is not necessary that we will find these kind of exactly parallel sentences. But we would still find sentences with similar content, right? Like, for example, I would like to know the price of this car in English, and Hindi में मुझे ये कार पसंद है, तो इसकी कीमत कितने होंगे? Which would roughly translate to, I like this car, what would be the price of it? So even though the sentence, the words, everything are dissimilar, they are different, the content, the meaning of these two sentences are similar. It's more or less the same. This is called what we call as inherently parallel data. So, and inherently parallel data is more common in real world than one would expect, right? Articles on the same topic, like news articles published by same media house on a particular day in India. So there will be a Malayalam edition of a newspaper, an English edition of a newspaper, as well as a Hindi edition of a newspaper. And the news articles would roughly be the same, except for the regional page. And a dedicated kind of queries that a chatbot would receive for a particular for a particular use case. For example, banking. People can come and ask what would be the interest rate for a car loan in multiple languages, and that chatbot is expected to receive similar queries only, because it's not expected to cater to any other application. So the news categorization experiment that I was talking about was conducted as part of this initiative called Sahaj Labs, where we literally sit and do R&D and device solutioning for use cases. Here, we have actually successfully used a transfer learning. We fine-tuned XLMR model with Malayalam news data and actually obtained good accuracy in Tamil, Telugu, and Hindi, provided when we actually conditioned the Tamil data and Hindi data to belong to the same similar content. We restricted that our news data cannot go from from left to right end of the spectrum. They have to be similar content. So when we actually assured that condition of inherent parallelism in our data, that we observed successful transfer learning or successful cross-lingual transfer of knowledge from one language to another, provided that we used this pre-trained model called XLMR, which actually have seen language representation of all these languages under our consideration. Okay, so this was the first experiment that we first, not exactly first, but one of the first set of experiments that we conducted to explore the extent of transfer learning that can be provided by these pre-trained massively multilingual models. Right. Now we can talk about information extraction from short text messages. Up until now, the topic categorization experiment that we were talking about were actually on news articles. So to make one decision, the classifier had a lot more data to look into, because if there are 10 sentences in a paragraph, there are 10 sentence embeddings. There are 10 into X times word embeddings. Now, when we talk about short messages, it's just one sentence. So the problem becomes more trickier. And short text messages is again a relevant thing when we are talking about conversational assistance, text-based conversational assistance. Okay, let's look at the study case. Conversational assistant for the sales support scenario is what we took as our study case. This is an intelligent assistant which can understand the customer queries and answer intelligently, provided the customer queries are related to one particular application. For example, if I am a business owner and I sell washing machines and I have a conversational assistant, my expectation is that conversational assistant would receive queries only related to washing machines. Multiple type of washing machines. People can come up and ask what are the color options in this washing machine, how much is the capacity of the washing machine, etc. And so on and so forth. So this is a very dedicated assistant which is supposed to answer one particular set of customer queries related to a particular setting, a particular application. So stages in building a conversational assistant are basically we need to first receive the customer query. And then we have to, if once we receive the customer query, we need to do an intent classification, intent recognition, right? I would like to know what is the intent of that customer. And the intent in this particular setting will be a closed set of intents. It won't be an open set. So a user can come, a customer can come and ask me about the color options of the washing machine, the price of the washing machine, the capacity of the washing machine, etc. Right? So there are only like so many intents that a customer can ask pertaining to this one particular application. So intent classification, what exactly is the customer asking for? What is the intent of the customer? What is he trying to find out is part of intent classification. Now, entity recognition is again another task. So entity recognition and intent classification can be together known as information extraction for a particular conversational assistant. Entity can be closed set or open set. So a customer can come and ask me about one particular model of that washing machine. So that model becomes an entity. I would like to retrieve that information from the user message so that I can, the assistant can give the appropriate answer. So this customer is asking about this particular model of the washing machine, and he is also asking, his intent is to find out the price of the washing machine. So these two things clubbed together is called information extraction from the context of a conversational assistant. So basically, we have to understand the meaning of the query and we have to pick relevant details in the queries so that intelligent responses can be generated. And of course, the next part is generate response to give it back to the customer. So this whole study, we used the RASA framework to implement and experiment with the chatbot setting or conversational assistant. Now, as I was discussing earlier, right, we did not experiment with pre-processing as well as post-processing because those are non-language dependent things. So the focus was again on natural language understanding, NLU. And in this particular talk, I will be only talking about intent classification for the conversational assistant use case. NLU is again understanding the customer query, understanding the user query. For our particular experiment or research experiment, we have received short user messages which are belonging to 13 different intents, and we made sure that for the fine tuning or the training data, we have 150 user messages for each intent. So 150 times all these 13 intents are occurring in our data set. Now, just to hint on the complexity of the task, it is not very straightforward task as the news classification where we discussed about 4 or 5 different categories. Here we had 13 intents and 3 different type of intents, 4 generic intents, where a customer is coming and say, "Hi, I would like to know something. Bye, I am done. I got the information. Now I'm leaving." So these are the kind of greeting and goodbye wala intents, which are easier to classify. Then there are 5 individual intents. 5 individual intents are product details, a query about a product detail, query about a product price, color options, etc. I think, okay, it's not here, etc. And then there are 4 combination intents. Okay, combination intents are trickier in a conversational assistant setting. So a user is coming and asking about a car, for example, about a car. So he's trying to ask, okay, I'm interested in this particular car. What would be the price of it, and what are the loan options that are available? So most of the automobile providers have their own finance, right? So a user is coming and asking about loan as well as price. And there are 2 intents in that same sentence. So these are called combination intents, which kind of increases the complexity of the problem and the complexity of the data set basically. So it is very easier for a classifier to misclassify these combination intents to either a product price or a loan intent, because those 2 intents are also there in our 13 intents, right? So this is the complexity of the data. And labeled, we have a labeled test data, around 50 user messages for each of these 13 intents. Process pipeline is again straightforward. We have pre-processing, embedding extraction, which is we actually combined Embed and XLMR, and then there is a classifier, which is basically a couple of layers of fully connected layer and softmax. Then output, we are actually tracking in terms of F1 score as well as accuracy in percentage. And we used adaptation of massively multilingual models, which are basically XLMR and Embed in multiple permutation combinations of the languages under our consideration. So to begin with, what we did was we have Embed and XLMR. The new Embed has 100 languages, 96 was the first version, and XLMR has around 110 languages. So what we did here is just to showcase, if we don't fine tune, if we don't do that domain adaptation and task adaptation, what will happen? So we took XLMR, no fine tuning, just tested it on intent classification. Our results are around 7% for English and Malayalam. And then we used that fine tuning data to fine tune XLMR and this whole pipeline of classifier. Our accuracy improved to above 90%. Similar behavior is observed for Embed also. And in a general sense, people know that XLMR performs much better than Embed, particularly in conversational informal scenario, just because of the fact that Embed has seen more formal sort of data, like in Wikipedia articles, or as opposed to XLMR, which has seen more informal conversational kind of data in tweets, in Facebook posts, etc. Because this is from common crawl, it is from crowdsourced data. So we focused only on XLMR from now on. Now what we did was we actually took Malayalam data because it was a personal choice. I am a Malayalam speaker. I could perform the data labeling and data validation, as well as I could perform the data validation for English. What we did was we fine-tuned XLMR progressively with Malayalam data as well as English data, because after data analysis, we found that there are English code switching happening in our customer queries, as one could anticipate, right? Because people are talking about names of multiple products, price of multiple products, and terms like loan, EMI, etc. These things will not as widespreadly used in one's own native language, right? So we actually progressively fine-tuned XLMR-based pipeline for intent classification using Malayalam data and English data. Now, unsurprisingly, English and Malayalam gave 90%, above 90% accuracy for intent classification in these 13 intents. Now, what we observed was it actually gave faithful performance in Hindi, Tamil, and Telugu also. Okay, because we made sure that the inherent parallel nature of data is present because it's dedicated customer queries received by a dedicated conversational assistant for sales. Okay, so what we found was when we did no fine tuning with XLMR, this is the data, this is the accuracy around 7%, 6%, 6%, etc. for multiple languages. We just showed that model or a pipeline with XLMR, some data in Malayalam and some data in English, and our accuracies skyrocketed to 93%. Some 72%, 70% are also here in Tamil and Telugu, but remember that it is zero shot learning. We didn't do any fine tuning, any training with respect to Tamil as well as Telugu data, and still we got faithful performance. So this is the power of transfer learning and using massively multilingual models. So massively multilingual models have already learned all these languages in a general setting from the data that it has seen. Now we are doing task adaptation with respect to and also language cross-lingual adaptation with respect to one particular language and one particular task, and it is able to successfully deliver the transfer learning capability to other languages, provided that the task remains the same and the data domain remains the same. So this is the result. So let's wrap up. So conclusions are pretty straightforward. The massively multilingual models put out by Google, Facebook, they actually lifted multilingual NLP from nothing to awesome. And even with limited data available in some languages, not all languages under our consideration, with a minimum labeling effort, with a minimum data cleaning and validation effort, we can actually construct conversational assistants. So I just presented the results of just one task in the information extraction. We have actually similar results in the other tasks also. So to actually build a multilingual conversational assistant, we can use massively multilingual models fine-tuned with minimum efforts in terms of data preparation, in terms of adaptation, training, etc. And we can actually port or transfer this knowledge across languages, provided that the data domain and the task remains the same. And we can think about multifold business applications, right? Sales assistant, conversational assistant for sales, conversational assistant for whatnot, all the kind of business that we encounter in our day-to-day life, public address systems, news archiving. News archiving has multifold of applications. It will be the same in news. It will be beneficial for research articles, which legal articles, etc. So there are multifold business applications. So thank you. I would like to thank my colleague Oshin, who was there with me throughout this entire research, who was also part of Sahaj Labs. We did this research together, so I'm presenting on behalf of both of us. So if you have any questions, please reach out to us. And also, if you have any questions regarding today's topic, shoot now.
Hi, Karthika.
Hello.
Yeah. So this is regarding multilingual model. So maybe means is there any possibility of developing universal model which understands? Suppose there are 5 languages. For that 5 languages, vocabulary content for that model, vocabulary contains all the words in those 5 languages. All the mannerisms for those languages will be modeled in that particular model, means all the syntaxes and semantics. So this will definitely, it will be a large insight, but it will give more accuracy than current state of art BERT and MLM kind of model.
Yeah, so basically this massively multilingual models are one step towards that universal modeling, right? But when you talk about universal models, of course, you cannot model the universe. So there are going to be some restrictions. So for a particular application in one's own hand, what are the restrictions that we can play around is actually the crux. So in our case, we had this conversational assistant, sales assistant in our mind, and how can we make the most out of the existing resources is what we study. And our study uncovered this whole notion of inherently parallel data because people generally overlook that aspect, right? When you're talking about conversational, any application, any NLP applications with cross-lingual transfer, this is not what people are looking for. But think about from a business application standpoint, right? This is more common than you ever imagine. This is going to be big, huge in a multi.
Yes, I quite agree with you. Second question is regarding accuracy, and so the accuracy results. So, don't you think those results are depends on training as well as test data?
Yes, of course. I mean, I wouldn't claim that it kind of solved all the problems in the universe, of course. So if you see that 70% accuracies that I have reported in the last slide for Tamil and Telugu, I am not a Tamil or Telugu speaker. So I couldn't actually do the data validation that was required. Now that actually one of my colleagues helped us out with the Telugu data, that 70% is also 88% now.
Okay.
Yeah.
Yes, suppose there are classes are similar. There is one class mismatch there in Tamil and Malayalam, I think. If classes are similar, then there will be accuracy will be quite high in terms of Tamil model,
Yes.
right?
Yes.
Okay. Yes. Thanks for this.
Thank you. Thank you for your
presentation. Yeah.
Hi, Karthika. Thank you for that very nice talk.
Hello.
I just wanted to ask, like, if like in the experiments, did you also try like multilingual fine-tuning on top of the these massive multilingual models?
We did with a couple of languages that also gave similar results. So I didn't put all the results today,
Okay.
but we have actually faithful results for unseen languages also.
Nice. Thank you.
Okay. If we don't have any more questions, I am on LinkedIn. My name is Karthika. Please shoot any questions, any doubts. If you want to collaborate, if you are interested in Sahaj, please shoot any one of us a message. Sahaj page is also on LinkedIn. I am also on LinkedIn. Please do keep contact. Please attend our future editions of DevDay as well. We have a variety of topics. We announce it on Meetup, and yeah, see you all in the near future.
Or if you are interested to give a talk, you can connect with us as well.
Yeah, sure. That too. Sorry for missing that. Please, if you are interested to talk about your work in any topic, please ping us for that as well. Okay.
Then we'll close the session. Thank you so much.
Sure.
Thank you, everyone.
Thank you so much. Bye-bye.
Thank you. Bye.
Bye.